Welcome, welcome, welcome. I am so thankful and honored to be joining you guys again this year. My name is Ronnie from Fun Weird Science. I'm based outside of Atlanta, Georgia, and it is an honor to be here with the 2020 Inclusion Collaborative. So today, guys, we're going to look at the importance of engaging children in STEM. Why is it important? Why is it important to engage kids in STEM to build their confidence so they can grow to be confident and competent and seeing themselves and having access to these opportunities will help to make our children more well-rounded and more phenomenal. So if you're on social media, check us out at Fun Weird Science on Facebook, Instagram, and Twitter. We would love to connect with you. And let's hop into today's discussion. Now, I know you're wondering who this guy is with all this hair on his head. Well, that was me a few years ago. And that lovely young lady sitting next to me, she's now my wife. We've been married now 18 years, and we have 3 amazing children that we are preparing to send out into the world to be change agents. Our oldest daughter is a junior in high school. She loves computer science and law. Layla is our second eldest. She loves journalism and basketball. And little Ronnie is just glad to be here to join the party. When I'm not doing STEM and science, my hobbies are zip lining and whitewater rafting. But now I get to travel the world. I've taught the last 20 years in school, and now I have a chance to travel the world and work with communities like yourself to show how making STEM exciting and engaging puts us in the ideal position to service children. So I'm going to talk to you today about the 3 reasons why students must do STEM or STEAM or science. Number 1, it allows them to build confidence and competence. They are able to nurture their authentic curiosity. Kids are very curious. So we have to definitely make sure that we're being mindful of serving and meeting the different needs of our children, whether they are visual learners or they need to touch, they're more tactile, but making sure that we're meeting the needs of all of our students, because we don't want our schools to be somewhere that creativity goes to die. So number 1, it allows kids to nurture their authentic curiosity. In too many of our classrooms, kids are reading about science. And in order for science to be engaging, they have to do it. We no longer can afford to just give children information for them to hold it and then spit it back out to us. We have to allocate the appropriate time to engage children in science and STEM, and not teaching it in isolation, but finding ways to teach from a transdisciplinary approach throughout the curriculum and throughout the school day. Second reason is because it allows children to make real life connections. Nothing makes learning more appealing than when learners are able to see how it connects to the real world. Now, in this picture, many of you all would be okay if I told you that this is a picture of an airplane going to Alaska in December, right? We would be okay with the empty plane traveling to the coldest place in the country during the coldest time of the year. But this picture also represents the millions of jobs that are going to go unfilled because our students aren't getting, in some institutions or some educational school systems, not in Santa Clara, of course, but if kids aren't given the skill set or the opportunity to engage in STEM and build that confidence and develop those soft skills, then they risk being in position to fill the millions of jobs that will be available to them once they become adults, or entrepreneur opportunities. So these empty seats represent jobs, money, and living. Research shows that STEM jobs are increasing, and the hourly wage is increasing. Out of 100 careers, 93% of the wages in STEM career fields are above the national average. But through a recent survey, the U.S. finished 38th out of 71 countries in math and 24th in science. This is why it's urgently important that all students, regardless of what obstacles they may have along their educational journey, all students must have the opportunity to do STEM, to do science as early as possible in a positive, inviting, and nurturing environment. 33% of high school students are not prepared for collegiate science. And my favorite reason why we must do science or STEM, it allows our students to see themselves as problem solvers. Early exposure is key. Early exposure is key. Developing those soft skills. Here, my daughter Layla is in front of 500 plus adults, sharing her opinion about the relationships in our world between different countries. And this confidence came from her engaging in STEM. STEM helps to develop students' confidence and competence, and these soft skills in communication can manifest itself in other areas of their life. This is one of the proudest days of my moment with her sharing her thoughts about the world relations. Here's our oldest daughter this summer. She just finished competing in the Harvard Diversity Debate Challenge. And once again, having the chance to demonstrate her confidence in areas outside of science and STEM in a sense, but getting the competence and the competence through STEM engagement early. Through STEM engagement early, kids can develop those soft skills, communication, logical thinking, critical thinking, and those skills are transferable. Now, here comes the part that I've been waiting for. I am going to demonstrate for you a few ways to hook students' attention using hands-on science. Now, before we do that, first we have to stretch our brains. So hold your thumb like this. Let's get a full camera shot so we can see clear. And point to your thumb like this. Now, when I count to 3, I want you to repeat the motion of my fingers. 1, 2, 3. Now, what we're doing, we're forcing the left and the right side of our brain to work together. So if you're having difficulty doing it, it's okay. Lots of people do. But as we remind our children, good, better, best, never let it rest until your good becomes your better and your better becomes your best. So keep practicing that and keep trying that. Now, in my hand, in the chat box, tell me, what am I doing to this paper towel? What am I doing to this paper towel? Also, tell me what's changing. You notice what I'm doing, but what's changing? What about the paper towel is changing? What are some of the feedback in the chat box? Now, if you said that I'm folding it and the size and shape is changing, then you are totally correct. Can I reverse this change? Can I make it look like it did in the beginning? And the answer would be yes. This would be an example of a physical change, a change to the size or shape, but you can reverse it in many cases. Now, based on what you know about science, what would happen if I were to light this paper towel? What would happen if I were to light it? What 3 things would we see that lets us know that that paper is on fire? Did someone in the chat say we would see smoke? Then you're correct. Did someone say that we would see fire? Then yes, you're correct. And if you said that we're going to see ash, then you are correct. Now, here's the big question. Can I reverse it once I've burned it? And that answer would be, yeah, no, I couldn't. You're correct. If you said no, then you're correct. I cannot reverse it. and that would be a chemical change. But every now and again, something pretty amazing gets discovered. Here in my hand is a piece of paper, but this paper has been chemically altered. What do you think would happen if I burn this paper? Make your hypothesis in the chat. This paper has been dipped in a special acid, and I would love to see or hear what you think is going to happen when I burn it. What's some of the feedback in the chat? Awesome, awesome. So we know that there is a slight delay. So I'm gonna make sure I don't go too fast and give us a chance to communicate with that delay. You know, that delay made me think about NASA's complication with landing the rover on Mars. There is a delay, like a 7-minute delay between the computers on Mars and the computers back on the Earth. So for 7 minutes, they have no clue what is happening with the rover. So that 7 minutes of terror is a really good video to check out. So if you said that this paper will burn and smoke like a napkin, we're going to see. All right, here we go. 1, 2. Where did it go? Where did it go? That never ceases to amaze me. That paper is called flash paper, and it's been dipped in a special nitric acid, also known as nitrocellulose, and it burns instantly without smoke or ash. Imagine how cool it would be to come in the classroom and do that, and then sit down or walk out. I think walking out would be even more epic. But giving the students the challenge to write a story on where did that paper go, to be a great chance to give children a chance to express their creativity through writing, but having them create a story on where that paper went. Flash paper burns instantly without smoke or ash. Now, as a kid, my mom and dad would always tell me to not burn my money. What do you think they meant by that? What do you think they meant when they said don't burn your money? What do you think they meant when they told me to not burn my money? Now, what do you think would happen if I burned that? Do you think they meant don't burn it with fire? Nah, I think they meant, to not spend it unwisely. Don't spend all your money in one place, right? What do you think would happen if I were to light that dollar on fire? Put your hypothesis in the chat. Put your hypothesis in the chat. What do you think would happen if I were to burn that dollar? Yes, correct. Now, if I were to burn that the way it is, what do you think would happen? If I were to light this on fire, what would happen? What would happen? If I were to burn this bill, what would happen right now? Will it char like a napkin, or will it disappear like flash paper? Oh, the washing machine. Interesting. I am going to saturate that bill in a solution. Now, if I burn it the way it is, then we know that it will char and burn and smoke. But what if I were to take a solution like alcohol? I'm going to measure out some alcohol in this science tube. What do we call this science tube? What do we call this? I always love having a conversation with the students with vocabulary, science tools, identification, just to keep the conversation moving in a productive way where they're learning and not just by with their hands, but they're also talking about it and thinking about it. So I'm going to measure out, yes, if you said graduated cylinder, you're correct. I'm going to measure out 90 milliliters of alcohol. Now I'm going to take that alcohol and I am going to pour it into this cup. Now I have alcohol in this cup, and if I were to put the money in here and burn it, what do you think would happen? What do you think would happen if I just put it in the alcohol and burned it? All right. Yeah. If you said it was burned, then you are totally correct. Alcohol is very flammable. So I think it may be possible if we add some water. So I'm going to go ahead. Oh, interesting. I'm going to add 30 milliliters of water into our cup. Now we have a solution that cannot be separated. I love reminding the children that a mixture like trail mix, you can add things together, but you can separate them. A solution, on the other hand, cannot be separated. So I am going to saturate this bill and then take it out and burn it. All right, here we go. 1, 2. The bill burns, but it does not char. It burns, but it does not char. Why? Why didn't the bill burn and char? There are some areas on the end where it charred a little bit. I wonder what caused that to char and not the entire bill. What do you think? Share your thoughts. Share your thoughts. Yeah, you're totally correct, guys. The alcohol is what you saw burning, but the water protected the bill and kept it from burning. So what you saw burning was the alcohol on top of the water, and once it evaporated, the flame went out. So I wonder if the dollar is made from paper and the napkin is made from paper, what would happen if I put the napkin in the alcohol and water solution and lit that? What do you think would happen then? So now I have saturated the paper towel in the alcohol solution, and now we're going to light it. I wonder, would there be any difference? If you said the paper towel is more absorbent, you're right. It will soak up more alcohol and water solution. Here we go. 3, 2, 1. Look how tall. That's a very tall flame. It burns a lot more intense, and it's also burning for a longer period of time. So I see that there are some areas. Yeah, there are a couple areas where it was going to burn because it didn't get, I guess, enough alcohol and water. But look at the bill itself. The napkin itself is largely unfazed by the flame because what you're seeing burning is the alcohol. Just think for a moment. By doing those demonstrations, think about what conversations you will be able to have with your students and what they will be able to discuss amongst themselves. On a scale of 1 to 10, 10 meaning, man, my children would love this. 1 meaning, man, this is so unengaging. Give me some feedback in the chat. On a scale of 1 to 10, what do you think your children, what do you think they would think about these demonstrations? Or do you think they would create excitement within them? All right. So we're gonna keep moving because I don't want you guys to catch up with the delay. Awesome. And then have that moment where I'm just sitting here looking at the screen trying to wait for the catch up. So the next demonstration is called the whooshing bottle. The whooshing bottle. Check this out. What would you say is inside the bottle? What's inside the bottle? If you said nothing, think again. If you said air, then you are totally correct. All right. Now, when I put my hand on the bottom, what shape am I making? Yes, a circle. As I am up top also. Now, we call the distance around a circle what? And once again, I'm only modeling how I would have a conversation with the students, not to insult anyone's intelligence in this session now, but just modeling how I would have a conversation with the children, focusing very heavily on vocabulary words and making those different connections, right? So the diameter of the bottle is bigger where? At the top or the bottom? Yes, the top. So that means if we all were in the same room together and we tried to go through a small door at the same time, what would happen? Yeah, we probably would get stuck. It would be too many of us to get through that small opening. The same thing happens here. We know that when the circumference is small, the pressure tends to build up. Think about a regular water hose compared to a pressure washer. Because the pressure washer's nozzle is smaller, it will come out with more force. All right. Here's a good chance to go and research Old Faithful. Inside Yellowstone National Park, there's a naturally occurring geothermal activity where the pressure from underneath the Earth's surface finds an opening, a small opening, and forces air through the water, causing the geyser to shoot up. So small openings, more pressure. So what do you think would happen if I were to put alcohol in this bottle and then drop a lit match? What would happen if I put alcohol in this bottle and then drop a lit match? Tell me in the chat, what do you think would happen if I put alcohol in this bottle and then dropped a lit match? All right. While you're thinking, I'm going to measure out some alcohol. I'm going to measure out 90 milliliters. I know it says about 60 to 30 or 30 to 60, but because I've been using this bottle over and over again, sometimes even when I rinse it out, the effect starts to deteriorate over time. So I'm going to pour the alcohol in the bottle. There's already air in there. Now I have alcohol in what state? Correct. In liquid form. Okay. So I am going to cover the bottom and the sides with the alcohol. Now I can smell alcohol. So what state would that be? Gas. Yes. What do you hypothesize is going to happen when I drop a match inside this bottle? When I drop the match in, what color? What would we see? What color, if you're saying the flames are going to be on the inside, what color would the flames be? what color will the flames be? What are they saying in the chat on that one? What color will it be? All right, so maybe it may be blue. What other colors could it be? All right, now what sound do you think we're going to hear? Now, I can't hear you, but I want you to make the sound with your mouth that you think we're going to hear when we conduct this demonstration. Now, if you hear this sound, that doesn't have anything to do with our demonstration, okay? That is somebody on your side of the camera. So if you hear that sound, I want you to look to the left and look to the right to figure out where that came from, but it wasn't from me. All right. So safety goggles are on. I'm going to get my match ready. Let's see. That angle may be good. All right. Let's see. They say the only way to know in science is to test it. So let's see. In 3, 2. I don't know if you can hear that, but that sounds like a jet engine blasting. Sometimes it's so forceful that the air will shoot the match out of the bottle. So what happened? When I dropped the match in, we created what's called an internal combustion. All the air inside the bottle got forced out, and the air outside the bottle is getting sucked in. So we kept getting that whooshing effect until all the alcohol evaporated. So if the alcohol evaporated, what is this wet stuff? You're right, condensation. So when the alcohol evaporated, it cooled off and rose to the top of the bottle, and then it came back down as condensation. So this could be a really good opportunity to discuss the water cycle. And sometimes directly after doing this investigation, if you hold your hand here, the air pressure will start to collapse the bottle in some cases too. So there are lots of cool connections you can make with that whooshing bottle demonstration. Give me one. I just did it at home. Yes. But I would never encourage my children or tell my wife that I'm down here blowing things up in our basement. But I would never encourage the children to do that at home. It can be very dangerous. But if you're going to do it at home yourself, I highly recommend using long matches so that when you're getting ready to drop it in, your hand is clear of the danger zone and you don't get burned. All right, but give it a try. Research it. Look it up. The whooshing bottle internal combustions. Now, I'm jealous of you, California dreaming, living, wonderful people, because you guys very seldomly get very cold weather, right? And I know in some parts it can get a little chilly and windy, but here in the South, it can get a lot colder as well, right? And I notice sometimes, tell me if you've ever noticed this. Have you ever gotten into your car and it's cold, it's winter time, and there's a light that comes on that says tire pressure low? Ever had that happen before? I am going to use a balloon to represent my tire. I'm going to fill that balloon with warm air, right? I want you to tell me, how can I make that balloon change? Think about that. Now, here is my balloon. This balloon represents my tire. Now I am filling that balloon with warm air. And we know that when air molecules are warm, they tend to go really crazy. They spread out. And that's why my balloon is inflated. How can I make the air inside this balloon colder? How can I make the air inside this balloon colder? How can I make the air inside the balloon colder? What do you think? Can I put it in the refrigerator? Can I hold it over the air conditioning vent? Can I put it in the freezer? I know. Should I rub it with a handful of ice cubes? What would be a great way to make the air molecules in this balloon colder? You guys may be in luck because here at the Fun Weird Science Studios, I think we have something that we can use. I have a substance that is really cold. What are they saying in the chat room? Have they given any suggestions? Fridge or freezer? What about some liquid nitrogen? What about liquid nitrogen? I'm going to pour some in the bowl. What do you think would happen when I put the balloon inside this bowl? If you said pop, maybe. Do you think the balloon will deflate or get smaller? We know that when warm air is in the balloon, it expands. So will the cooling of those air molecules make them smaller and contract? Let's see. This stuff is so cold. If I put my hands in to make direct contact, it could freeze my hands. So I'm going to be very careful not to touch it with my hands. I'm going to use a cup to push it down, but I'm being very careful as to not put too much pressure because the pressure can make the balloon pop. If you hear that, the balloon now sounds very papery. And guess what? Oh man, the balloon is now flat like a pancake. What do you think would happen if I took that balloon out of the liquid nitrogen? What would happen if I took the balloon out of the liquid nitrogen? Let's see. If you said reinflate, let's see. Sometimes our kids give answers in class and their friends may snicker or laugh at them or make fun of them, and they may drop their head in shame or change their mind. Always encourage your children to stand on what they believe until someone proves them wrong. No matter how outlandish or silly the idea sounds, tell them to stand on what they believe. So now the balloon comes out of the liquid nitrogen. And as you can see, the balloon is starting to reinflate. As it warms up, the texture of the balloon changes back also. But now the balloon has reinflated to its original size. Give me one word that describes what your children may say seeing that. And with that, I throw some of that back behind me, and now I have a really cool hat just in time for summer, guys. Now, This next one is really special to me because I have a friend who's an elephant and he wants us to make elephant toothpaste. Now, to do that, we need a few ingredients. We're going to need some peroxide. Now, this is not the peroxide that you want from your local drugstore. This is the peroxide that comes from a hair salon, and I'm using 40 volume. It would be a really great experiment to have 40 volume, 30 volume, and 20 volume to see what is the difference in the reaction time and strength. So I am going to measure out 1 cup of peroxide. You want to be very careful when handling this stuff because it can burn the upper layer of your skin. It can burn the upper layer of your skin. So be very careful when handling peroxide. All right. So I went ahead and added a little food coloring to it. I would encourage you to add food coloring because it gives it more aesthetics. It helps us to see it. In the chat, type in the science name for water. Type in the science name. What do we call water in the science community? What is the scientific name for water? If you say H2O, then you are totally correct. And the scientific name for peroxide is H2O2. What we're going to do is try to release one of these oxygens. We're going to try to release one of these oxygens and then catch it. Now, to catch it, we need some dish detergent. All right. So I'm going to give a nice teenage squeeze of dish detergent. I say teenage squeeze because my daughter likes to use almost half the bottle of dish detergent for 2 cups and 1 plate. All right. So we're going to use the soap to catch the oxygen. Now we just need something to release the oxygen. We need a catalyst. We need a catalyst. I think a great catalyst would be dry yeast. What is a catalyst? A catalyst is something that sets things in motion. You can make a nice tie-in to social studies or current events and talk about how Colin Kaepernick attempted to be a catalyst to get a conversation going in our country regarding the treatment of African Americans, right? So just finding ways to incorporate other subject areas all through science and STEM. That's that transdisciplinary approach. So we're going to need a catalyst to get this thing off and going. And a great catalyst to use is dry yeast. So I am going to measure out 1 tablespoon of dry yeast. And I am going to add 2 tablespoons of room temperature water. Now, you don't want to add warm water because that warm water will start to process and activate your yeast. All right, now I'm going to stir it up. And if I wanted to smell it, should I do this or should I do this? Should I smell it with my nose or should I use the wafting method? I always encourage your kids to use the wafting method in science to smell. Never smell like this because you can burn your nasal passage. So I am going to use this science tool. Starts with a F, rhymes with tunnel. What do we call it, boys and girls? Funnel. Good job. Good job. So I'm going to pour this yeast in and quickly move away. So in it goes, and look, coming out at a very fast pace, we have elephant toothpaste. And if you look closely, you'll see steam coming off. That's because we're making an exothermic reaction. Whenever you mix things together and it produces heat, that's called an exothermic reaction. And the kids love to put their hands in this. It's very warm and very fulfilling. And once the reaction takes place, there's no risk of burning your hand, as we mentioned in the beginning. What are your thoughts? What are you thinking? I think, I wonder. What are you thinking? What are you wondering? Would your students benefit from engaging in science and conversation and STEM in this way? Do you think that this type of engagement would make your day more enjoyable? And we know when we're having fun, time flies. So imagine having an opportunity to create this type of environment in your class every day. Imagine the gains your children will make when they see the relevance, the meaning, and the joy in their teacher in teaching these contents area or these demonstrations. It's a win-win, guys, and we help to increase the children's confidence and competence when we make the learning fun and engaging and relevant. Now, if you have any babies in your home or in your family, you know that you're going to love this next demonstration. So here we have 3 cups, and I need your job to help me keep track of where I put the water. This is called baby cups. I'm going to put the water in this cup right here. All right. 1, 2, 3. Keep an eye on the cup with water. Keep an eye on the cup with the water. Is the water in 1, 2, or 3? What would you say? If you said the water's in 2, then you are correct. All right, keep a track on the cup with the water. Is the cup of water in cup 1, cup 2, or cup 3? You guys are good. If you said 1, then you are correct. Last time, guys, keep a track of the cup with the water. Keep your eye on the cup with the water. Is it in 1, 2, or 3? If you said 1, there's no water there. There's no water in 2. So it has to be in 3, but water that comes out of this cup either. Where is the water? Where's the water? Inside this cup, we had something called sodium polyacrylate. Now, this stuff is what we call diaper powder. So inside the cup was this polymer that absorbed the water. So that is what prevented it from pouring out. So if we know that this polymer is used in diapers, what challenge your children? What other real world application could we use this for? How else could we use this polymer in the real world? How else could we use this polymer in the real world? Now, our last demonstration. Our time goes by so fast, but our last demonstration, I want to give you guys a challenge also. It's called the egg drop. What would happen if I took a cup and put some water in it? Let's change this camera around. Right? A cup with some water in it. And then on top of that cup, what if I put a pan? A pan. What if I put a pan Hold on. There we go. So on top of that cup is a pan. And on top of that pan, what if we put a paper towel roll? And on top of that paper towel roll, what if we put a raw egg? A raw egg. Now, the story goes there was a guy sitting under a tree and an apple fell down and hit him in the head. And he began to wonder what made that apple fall, right? Who is that guy? Who am I referring to? Who am I referring to? If you said Sir Isaac Newton, then you're totally correct. He came up with three laws of motion. But guess what? History teaches us that before Sir Isaac Newton, there were groups of people building pyramids, and some of those pyramid pieces weighed over 2 tons. And there's no machine that can lift the weight that some of those parts of the pyramid are today. So before Isaac Newton came up with the three laws of motion, this is a great opportunity to teach our children about the great wonders that were built in Egypt, or as the indigenous people refer to it as Kemet. All right. So here's the question, friends. Will the force of the broom be strong enough to make the egg go in the same direction? I'm going to pull the broom back and let go, but the broom is going to be stopped by the edge of the table. The pan is hanging off the table. So when the broom hits it, it will get stopped by the table. The pan will go in the same direction as the broom. Where will the paper towel roll go? Yeah, it may fall backwards. And where will the egg go? That's the big question. That's the big question. All right. Now I am going to pull my broom back. This may work, it may not. This would be a great science fair project on probability. Get a dozen of eggs and see how many chances or how many times you can get the egg to fall in the same location. All right. I'm going to pull back. I'm going to let go in 3, 2, 1. Oh, he shoots. He scores. And ladies and gentlemen, the egg went in the cup. The egg went in the cup. And that is fun. That's weird. And that's science. Now, before I jump off, I want to give you your challenge. You were asked to get some materials: cardboard, push pins, rubber bands, skewers or dowels, straws, recyclable materials, right? Duct tape, scissors, or some extra things you may add to it. But try to find recyclable materials and your go and a ping pong ball. Now, if you don't have a ping pong ball, you can ball up some foil to make it around the same size. Your goal is to use the engineering design cycle and build a structure that can stand by itself, right? And it must use either a pendulum swing or a rubber band pull to be able to kick or move that ping pong ball. Or you can use a combination of both, the pendulum and the swinging, or this pendulum and the rubber band. But your structure must stand by itself, and it must be engaged to hit and move a ping pong ball. Hit and move a ping pong ball. All right. Now, I can't wait to see what you come up with. Please send me pictures. Tag me on social media at Fun Weird Science. I would love to see it. If you're trying or doing any of these things in your classroom, please tag me online. I would love to see how your children are engaging in this type of approach. Hands-on learning helps to build confidence and competence in kids, and it increases their performance at school and at home. And if they can increase their performance at school, at home, then that will translate into their community, and that will spill into their city, their state, their country, and the world. Thank you so much for your time today. I'm writing from Fun Weird Science, and I am crazy about science. I'll take a few questions. If there are a couple of questions in the chat, we'll give a few moments for those. Anyone have any questions? Any questions in the chat? Awesome. Good stuff, guys. Thank you. Thank you. Thank you. Thank you. I can't wait to come back and join you guys in real time, face to face, so we can high five each other as we join this journey to get kids excited about learning science.